Hi, I'm Marta Martinez from IMST in Germany and chair of the Cost Vista Action. In this last presentation of the 5G challenges in antenna design, we will deal now with the components that will be needed for future mobile communication infrastructure and also for the terminals. We have some key issues that have to be addressed if we want in 5G to move to the millimeter wave region. First of all, and it's very important, is to see that nowadays there's only a limited number of components that are available as commercial off the shelf. For example, power amplifiers, low noise amplifiers, mixers, etc. Also, we don't know yet which is the frequency that will be selected for 5G millimeter wave communications. And depending on the frequency, we will have a specific frequency, bandwidth, and power requirements. We will need, for mobile communications, different requirements from what we were used to in, for example, satellite communications. We will need power amplifiers with higher linear output power. We will need high linearity receivers, low phase noise local oscillators, new phase shifters, etc. With that, we have to rely on the advances that are taking place in MMIC design. Mostly in silicon germanium, which has a power handling capability which is still not enough for the applications we are considering here. Gallium arsenide, in which the price is quite high for mass market applications like 5G, gallium nitride, etc. We are hoping that in the next years, the maturity of these technologies will allow us to have components for the mass market and to develop the new applications. Other key issues are the availability nowadays of very few adjustable components at millimeter wave as a commercial off the shelf. We will also need additional components like additional logic, for example, drivers, digital analog converters, latches, shift registers, etc., which will need to be designed and also integrated in our front ends. We also have the problem that the filters are not available as commercial off-the-shelf components. We will need for each development customized designs of filters and to deal with the problem of the size. So filters take place and they have to be integrated in highly integrated front ends. We will also need additional logic for the steering and calibration of our antenna front ends. We need for that additional mounting space and also for the routing of the lines, the steering lines and the calibration. We also will need to be careful with the size because when we are integrating these components, we will need to have some cavities in the RF materials that we are using. You can see, for example, here how we can integrate the mixer, the filter, the power amplifier inside the cavity with the feeding lines, the data lines, etc. We will need, for example, bonding between the different chips. We also need some decoupling capacities, etc. Also, if we are moving to the millimeter wave region, for example, in the Ka band, the distance between two elements, if we want to perform beam steering, the distance between two antenna elements will be around 5 millimeters. You see, if between two different cavities we only have 5 millimeters, we have to pack very densely all the components and put them into these cavities. Of course, you also have to take into account not only the size of the cavity, but also how to glue the MMICs inside the cavity. You use for that specific glues, and you have some kind of dicing accuracy. You have also the positioning and gluing and milling accuracy. You also have the tolerances in the design of the cavity itself. All this has to be considered in the design of the front end. One option to make it easier, the integration, is to design dedicated MMICs for each single application or each single system. With that, we could improve the integration density. For example, using one single local oscillator for multiple transmit and receive chains that are included in a single MMIC. It makes also routing within the RF PCBs much easier. We also reduce, by using these dedicated MMICs, we reduce the number of RF connections, which has the advantage of improving the performance the RF performance because we have less RF losses. We also have improved reliability, because every time we have a connection, an interface, that's a problem of reliability. We also have the cost issues. Active components sum up to 80% of the total cost of the RF front ends and the antenna front ends. If we can reduce the number of MMICs, we can also lower the cost of the final system. Also, for high production volume, the cost is determined by the area of the chip on the wafer. So if we can integrate 4 transmit-receive chains in a single MMIC, we will have a much smaller area on the wafer than if we have 4 different chips for that. And that would also contribute to lowering the cost of the whole system. Here is an example of a dedicated core chip that was developed, for example, for SATCOM. Here we can see that a single chip, which was developed by IMST some years ago and produced by OMIC, integrates a 2-stage LNA cascade with a phase shifter. We have also the 4-bit phase shifter, a 5-bit shift register, a 4-bit latch, and the digital input-output buffers. All this in a single core chip that you can see here. This allows for a highly integrated design of a phased array. If we could do the same thing for mobile communications in the millimeter wave, this would be a step ahead in the development that we are addressing. There's an issue there also, is that each chip may have to be designed for a specific system, a specific manufacturer, etc., which may be which can imply high non-returning costs at the beginning of the development. But if the production volumes are high enough, this may be a good solution to facilitate the integration of the system. Well, if we are going to the millimeter waves, we have seen there are many challenges, but maybe we can have some design tips. What can we do to make the design easier? First problem that we are facing is that the RF interfaces are quite lossy and difficult to design. So, as we see, we will have to keep the RF connections as short as possible. That means putting the stage, the frequency conversion stage, for example, the mixer, as close as possible to the antenna so that we minimize the RF paths. We also have the problem of lack of mounting space and the heat issues due to the high degree of integration. For that, we will need to use the MMICs in die form, that is with no package, and also to design an accurate thermal management. Here we will need to have the input from more experienced designers that know the problems from thermal management. So it's not only electromagnetic design. We also need to have the problem of assembly and build-up. It has to be suited for large production volumes and not only for the laboratory. So we will need to use standard PCB materials whenever it is possible, and also consider only proven manufacturing technologies. Maybe in the future we can go to more innovative solutions, but for the first steps of the mass market, we will also have to rely on what is sure to work. So, in summary, with the advent of 5G, we will have new bottlenecks, dealing with the integration of a large number of components, with the heat management, etc., and the availability of the components themselves for the frequency bands we are dealing with. So, the availability of cost-efficient components will be capital for mass market deployment. Thank you for your attention.